So today we will talk about sampling of analog signals using microcontrollers. If you have studied signal processing or signal theory, some things will be very familiar to you and known, but we'll just put it in this context of microcontrollers. So sampling of analog signals using microcontroller, MCU, signals. Okay, so we will do it through an example, or maybe two examples in parallel, and we will just check out what it means. So you usually have a microcontroller, and you want to sample some analog signal, and maybe you want to just sample it and send it to server. Maybe you want to use it for some control. I will show you an example with temperature controlled heater, which has to maintain a constant temperature in some liquid. Maybe it's for some evaporation or something like that. But you sample temperature and you want to heat something and keep it in constant temperature. So it will look like this. You will have some heater. I'll draw it red. And probably the heater is just a big resistor. Usually that's how they're built. And so it has some power supply. Usually high voltage, maybe it's 230 volts, or in this case, we'll use low voltage to simplify the circuit, but maybe it's, for example, I don't know, 12 volts. I'll change it to 12 volts DC, some heater, and then you would normally use a MOSFET with which you turn on and off the heater depending on the temperature. And this MOSFET you would want to just connect to microcontroller. Microcontroller can turn the MOSFET on or off, and that's it. PN, so it's like this. Arrow goes there. Okay, so just to make a circuit complete, if the microcontroller freezes or maybe there's a problem in solder joints, people always put a pull-down resistor between MOSFET gate and source so that the gate is held low and discharged when the microcontroller is off or is in error state, so that the heater doesn't turn on itself. This circuit makes sure that the default state of this MOSFET is off. And this resistor, I'll write it, R1, and I'll write in small letters that it is a MOSFET pull-down resistor with size 10. Okay, so then the next thing that we can do is measure the heater's temperature. You can use some high temperature glue or use a screw and screw some temperature sensor to the heater. And we can, for example, use a sensor which is called PT1000. Okay. It means that its resistance is 1000 ohms at room temperature, 25 degrees. And if it gets hotter, it's made out of metal. Hotter metal has higher resistivity, and at lower temperature, it has lower resistance. So, its temperature changes the resistance. So I'll draw it with some thick line. It's right there. You can glue it, or you can use a screw and screw it somehow. Screws are usually better because glue can wear off in time, but if you screw it to the metal with some screws, usually they last much longer. And if you use metal clips, they are even better because they always apply some pressure. So metal clips are even better in this case. Okay, and this temperature has, in the simplest case, it just has 2 wires. So how can we connect it in some way that we get an analog signal to measure the temperature? So I will replace, I will draw it as a resistor so that, the schematic is clear, but basically this will be it. So a typical way how people do it is they put the analog signal with reference to ground. So this sensor is this resistor. It's temperature dependent. But usually people try to make the schematic in such way that the analog signal is reference to ground. So, it goes down, it goes closer to ground, so the level is lower, and it goes up. It means that voltage on its top part increases, voltage goes up, and the controller can detect it. And usually you would have some top resistor so that this point is somewhere in the middle of the microcontroller's analog to digital converter, and you can measure some voltages between ground and supply voltage. We will call this resistor bias resistor. It will be R2, it is bias resistor. So, it creates some reference or bias. If we just connected this temperature sensor to power supply, well, it will just always have voltage of 3.3 volts, for example, if we're using 3.3 volts. But now one resistor is fixed, and the other one changes, so this midpoint will go up or down. So this thing would connect to microcontroller's analog input. I'll just write it as analog in. Okay, and now we need to talk about some things in this circuit so that we can improve it a little bit. So first of all, as we know, this temperature sensor is located far away from microcontroller. So it's possible that some electromagnetic noise gets into these wires, and it actually creates a noisy signal here. And the second thing is the heater heats up, the temperature goes up, heater cools off, the temperature also goes down. So the signal is changing, and I'll just draw it. Let's say you heat it up, the signal goes up. So I'll draw the real signal in blue. So I don't know, the temperature goes up, it can also go down, more up, more down, like this. Okay, but the problem is that you can have noise on the PCB. Maybe if it's inside the car, then this supply voltage is changing all the time. Maybe there's some noise coming from outer world, and also the resistor also has its internal noise, which is called pink noise. It's just the noise which is inside the crystal lattice of the material. So these crystals are actually oscillating in temperature and they're making noise, and also some electrons are jumping into the into their spots around the nucleus and out of it, and this generates noise. So this actual signal that you would see if you connected oscilloscope is maybe like this. You know, very noisy signal. Maybe there is a high frequency component, for example, from if it's inside the car, let's say it's inside the car because it would make a good example. The car has a motor which is spinning at, for example, I think it's something like 1,000 rounds per minute, revolutions per minute. So there would be this one component imposed on the signal, maybe some other noise sources. And the problem is that if you're just sampling this analog signal at some speed, you can have a mistake in a sampling. Let's say you turn on your microcontroller. I'll just write it here, MCU. And let's say that you tell your microcontroller to sample the signal in, with some interval. You cannot sample it with infinite resolution. You can, for example, sample it with 1,000 samples per second, for example. The theoretical maximum is usually 1,000,000 samples per second, but you can only do it for a short time. Then your microcontroller's memory is full and you need to evaluate the data, do some signal processing, and then you can use it. So let's say we are sampling, and I'll deliberately sample in some bad way so that you see the problem. Let's say I'm sampling here, I'm sampling here, I'm sampling here, I'm sampling here, here, here. And as you can see, the microcontroller can accidentally sample in such a way that it samples the peak of the higher frequency. And maybe at some other point, it just happens so that it starts to sample these, lower parts. Of course, sometimes it will sample right in the middle, but it's possible that it samples higher frequencies. It's like, let's say you have your daily routine, you eat at 9 o'clock, 3 o'clock, and then in the evening at 8 o'clock. So if somebody calls you exactly at 9 in the morning and asks what you're doing, you'll say you're eating. If he calls you 3 o'clock and you're eating your dinner, and somebody calls you and asks you what you're doing, you'll say again that you're eating. And in the evening, the person calls you at 8 o'clock, they ask you what you're doing, you say you're eating, and the person assumes that you basically ate all day nonstop, because every time somebody calls you, you're eating. And it would look like you're only eating. And this is also the same in the signal processing, that you can accidentally sample signal too high. So, you're sampling and it just happens that you're sampling these peaks. So the signal that you think is the real deal is like this. And then after some time, it samples different location. And so as you can see, the blue that I sampled with my microcontroller is very different from the light blue, which is the real signal. Well, the blue is the real signal at the temperature, but the orange is the signal with noise. So The orange one would be like the real signal in the real world. So now we have to look at methods how we can get rid of this noise and get rid of this sampling mistake. So this sampling mistake is called aliasing. So when you are sampling something and you're sampling at this frequency, which is similar to some higher frequency, and you constantly get results of it's an aliasing problem, and this is why you need anti-aliasing filter, which will just be a low-pass filter. The solution will be pretty simple. But let's just look at this problem. So from the signal theory, you maybe know that if you sampled much faster, you would sample correctly. So let's say this orange is the signal. If I sampled, for example, instead of, every, for example, 1 millisecond, let's say I'm right now sampling at 1 millisecond. If I sampled, for example, 100 times faster, I would have 100 points in that 1 millisecond. So it will be 100,000 samples per second. I would be sampling the signal correctly, right? Because there would be more points and I would have the signal perfectly sampled. But if we would zoom in, this orange signal would have even higher frequencies. Even in here, it would just be, noise. Because noise usually has infinite spectrum. So sampling more oftentimes doesn't really solve the problem. It's possible that it does solve the problem, but, maybe the other thing is that you don't want your microcontroller to be overloaded with this sampling. Sampling 100,000 times per second means loading the CPU with lots of data, which needs to be, averaged out and compared and so on. So what people usually do is there is this rule, which you probably know from subject called signal theory, which is the Nyquist rule and Nyquist frequency. So the question is, how quickly should we sample the signal so that we don't lose any information? How quickly should we sample the signal so that we have 100% of the signal correctly sampled? Because if we're doing it rarely, we don't see higher frequency oscillations. So how fast should we sample it? Well, the easy and simple answer is you would want to sample it approximately at the frequency, which is the highest frequency in your signal. More precisely, you need to sample at 2 times the highest frequency in your signal. So sampling frequency should be 2 times highest frequency in your signal.
So this is the sampling theorem, right?
One more time.
This is the sampling theory, like
exactly.
Theory.
Yeah. Exactly. This is just simple sampling theory, and it's part of the signal theory. Yeah. So if you sample at twice the highest frequency in your signal, then you're safe. You will get 100% of the input signal. But let's say you take an oscilloscope and you measure and you find out that, for example, highest frequency is, I don't know, there's still some component in the signal which is at frequency 2 megahertz. Well, you can't even sample it with an average microcontroller. So this equation can actually be used in the opposite direction. So what you would do is you would make a decision that you want to, for example, sample at something like, I don't know, maybe 10 samples per second, and then you use a low pass filter to remove the higher frequencies. And the low pass filter will be such that it guarantees that the output frequency of that filter is at least 2 times lower than your sampling rate. So because you will look at this heater and you will measure its time response. So for example, you look at its step response. For example, you turn on the heater and then you want to know how quickly it heats up to the maximum temperature. So you turn it on and it's something like this, and you measure that it, for example, reached almost the top temperature within, for example, 5 seconds. So, you know, there's no reason to sample this temperature at 1 million points per second because the heater is so slow that the real signal is really slow. You don't want, you can measure it something like 10 times per second and it will be already a lot of points for this line. So if the heater is slow, if it has a lot of mass, when you heat it up, it's going to change its temperature slowly. So you don't have to make millions of samples per second to measure the temperature. So what you just do is you make a decision. For example, I'll write it on the side. Choose sampling frequency based on your there you guys. So you choose the sampling frequency based on your valuable signal, which is the signal that you want to measure, which is just temperature, not the temperature plus all of the noises that come on top of it. For example, 10 samples per second. And the second thing that you do is you just insert between your source of signal and the microcontroller's input a low pass filter, which has a time constant so low that it passes through no more than 10 hertz, or better say 5 hertz of frequency. So construct a low pass filter with cutoff frequency 1/2 of your selected sampling frequency. Okay, so in this case, if we're sampling at 10 samples per second, the filter should be such that the cutoff frequency for low pass filter is 1/2 of 10 samples per second is equal to 5 hertz. So, you know, a very low pass filter. Can you construct such filter? Most of the times, people don't construct some kind of crazy, complicated low pass filters. with operational amplifiers or something like that, usually people just use RC low pass filter. If possible, you would just put a resistor and a capacitor, and that's your low pass filter. And the frequency, I think the cutoff frequency was how much square root of R times C, something like that. We can check out it on the internet. So RC cutoff frequency. But I think it was calculated like that. Yeah, here it is, yada, yada, yada. Okay, that's a lot of. Okay. This time constant, or maybe it's 1 divided by RC, not the square root of R times C, because that is the time constant. I don't remember.
There is 2 pi RC, I think, 1 over 2 pi RC.
2 pi RC, this right?
Yeah.
Okay. Yeah. I don't remember, but you know, I can just find it on the internet. So 1 divided 2 pi, whoops, RC. Okay, so that's how you would calculate the value of R and C. You would just select some resistance and then calculate the capacitor from it. Or maybe usually people would maybe try it the other way around. They would select first capacitance, because large capacitance is more expensive. Resistors are always cheap. You can buy, you know, it doesn't matter if it's 1 ohm resistor or 1 kilo ohm resistor, they will all be basically the same. They will cost $0.01 per piece at 1,000 pieces. But capacitors, the bigger the capacitance, the more expensive it gets, right? So if you select capacitor, which is big, you will just pay more. So usually people will try to select capacitor, which is cheap and so smaller. And then this resistance value will be just increased correspondingly. So let's see. And the second thing is, in this circuit, you already have a resistor here. Let's say I put a capacitor here. To charge this capacitor, the current has to come from the left side, because the input doesn't give in or out the current. It is an input with high impedance. So to charge this capacitor, the current will flow through this top resistor. So some resistance you already have. So you actually can reduce this resistor's resistance by the top resistor value. And oftentimes, this is actually how people do. They just put a capacitor here, and for this RC filter, the top resistor is already the resistor that is used. Okay, I will make that suggestion a little bit later. At the end of the lesson, you'll ask me again, and then I'll show you. First, let's calculate the resistor in this example. So bottom resistor is 1 kilo ohm at room temperature, and this heater will, for example, heat up to no more than, let's say, 100 degrees Celsius. So we can go on the internet and find PT1000. Oops. resistance table. PT1000 is a resistor which is standardized, and it doesn't matter who produces it. If they write PT1000 on the sensor, it's guaranteed to have this fixed and predefined temperature and resistance relationship. So in this table, it says that at 100 degrees Celsius, the resistance will be 1,385.10 ohms. Oh, I already wrote it here at 1000 degrees. It's 1,385.1 ohms. 1,385.1 ohms. Voltage reference inside this analog, inside the microcontroller will be, for example, 1.1 volt voltage reference. So the analog signal should change from, from approximately 0 to 1.1 volt. So higher resistance will give higher volts. So we need to assume that at this resistance, there will be 1.1 volt. And from this, we can calculate the top resistor. Let's assume that the supply voltage is 3.3 volts. Knowing that the bottom resistor is 1,385.1 ohm, and midpoint resistance is 1.1 volt, can you calculate the top resistor? Okay, I'll give you 2 minutes to calculate the value of top resistor with these given values. Bottom resistor is this. This point is 1.1 volt. Supply voltage is 3.3 volts. And so you need to calculate the top resistor. So you can find this on the internet. The source voltage is 3.3 volts. Top resistance you don't know, so you leave it blank. The bottom resistance is 1,385.1. And the output voltage is 1.1 volt. You press calculate, and it says the top resistance is 2,770 ohms. In kilo ohms, it's 2.77 kilo ohms. This is how you can calculate it. Or you can calculate it by hand. But by hand, it's just slower. If you're working in some big company, they just want you to get the result fast. You need to understand that you can calculate it. You need to understand that you need to search for voltage divider calculator. But then you just input the numbers, press calculate, and it just calculates it for you. So the resistor in top is 2.77 kilo ohms. On bottom is 1.385 kilo ohms. I'll just change it to kilo ohms. And now let's calculate the capacitor value if we would just use only the top resistor for the resistance of the low pass filter. So from basic algebra, we can just calculate that, for example, C is equal to let's see, I just put C there and F in the bottom. So it will be 1 divided by 2 P, oops, P R frequency. And that will be 2 times 3.14 times resistor, which is 2,770 ohms, times frequency, which is 5. And then 1 divided by this value. And I'll multiply with, this will be millifarads, and this will be microfarads. So it's 11 microfarads. Okay, 11 microfarads isn't really that big of a capacitance. So let's go on the internet and try to buy a capacitor which has a capacitance of a little bit over 11 microfarad. I'll just write it down. 11 microfarad. Okay, so I suggest, well, I'll show you why I will use this red expert thing, but the company, one of the largest producers of capacitors is Wood Electronic. They have a website. Okay, I agree to their service, blah, blah, blah. And here, this Wood Electronic, they have a very convenient capacitor selector. So I selected multi-layer ceramic chip capacitors. And so I just check out what value I need. I need 11 or even more. I can take 12 microfarad if I want to. So in this filtering environment, I can select capacitance, 11 microfarad or more. And you can see that there are some capacitors, but there is one extremely important thing, which I have probably told you already. The problem with ceramic capacitors is that if their material is X5R or X7R, they have the problem that when you apply a voltage on the capacitor, which is what you normally do, you want to apply a voltage on it. It's crystal, because these plates attract, they compress the dielectric material between the plates. It compresses and it actually gets reduced the capacity of the capacitor. So at 0 volts, these capacitors really have capacitance of their nominal value, but when you actually put voltage on them, their capacitance is reduced. And good manufacturers don't hide this fact, and they actually are open about it. And for example, in Wood Electronic, you can check out this capacitance versus bias voltage, and they show you that, yeah, at low voltages under 3 volts, it's normal. But then if you apply a larger voltage, the capacitor's dielectric material gets compressed. It's a little bit piezoelectric material, and the capacitance goes down. And you can find more information about it on the internet. For example, Maxim integrated. So you can find this information in the internet. For example, one guy wanted to make an RC oscillator, but he noticed that his frequency was always higher. And it turned out it was because the input capacitor was a ceramic capacitor, and its capacitance lowers as the voltage increases, and so it started to oscillate at higher frequency. This article is really good by Maxim Integrated, which explains why your 4.7 microfarad capacitor becomes a 0.33 microfarad capacitor. Yeah, here it shows graphs of several capacitors, and the rule of thumb is larger size has less effect of this thing, but smaller size has bigger, more sensible effect of this DC biasing, capacitor crystal compression, and capacitance loss. So good manufacturers put these graphs. And so what we do is, for example, in this case, I take this capacitance versus DC bias voltage and I set it to the level which will be the working voltage of the capacitor. So if capacitor is connected right here, then the voltage on the capacitor will be 1.1 volt, or if this temperature gets lower, the resistance will get lower and the voltage will be less. So 1.1 is a maximum. And I set this slider to 1.1. I think I can write it here, 1.1 volt. And then it shows me the real voltage here. And in this case, all of these capacitors actually have a larger capacitance, but as you can see, smaller ones have bigger effect. For example, this 0805 package, it drops significantly. So for example, at 5 volts, the capacitance is only 7.3 instead of 22. But it's normal and it's the same for all manufacturers. It's not like Würth Electronic is making bad capacitors and Murata, for example, creates better capacitors which don't have this effect. This effect is determined by the material of the capacitor, which is X5R or X7R. They have this property. The only capacitors that don't have this property are NP0. As you can see, for example, NP0 capacitors, their material under this stress doesn't change the capacitance, but these capacitors max out at something like 1 nanofarad maybe. So if I select NP0 material and order the capacitance ascending, then the largest one that you can get is 33 nanofarad. That's the largest. We needed 11 microfarad, which is like 1,000 times more. And its size is really big. And it will be more expensive. This material, NP0, is more expensive because it's better. So that's just something that you need to take into account. And I'll write it down here. Remember to check capacity at working voltage. X5R and X7R capacitors have a capacitance decline under voltage. Yeah. So let's check out Murata. Murata website is SimSurfing. Murata is also a very good manufacturer. Their capacitor selection software is called SimSurfing, and you can select multi-layer ceramic capacitors. Okay. And capacitance versus voltage. So I need something between, I don't know, 11 microfarad and, for example, 22 microfarad. I don't want to have too much capacitance because more capacitance is more expensive. So as you can see, they have all kinds of capacitors. Their rating is X5R, the material type. Okay, they also have X7R and X6, but I think X6S is very similar. All of them will have this property. Okay, now it's slow. Okay, I'll select the first one here. I can go to capacitance versus, oh, here it is, DC bias. And you can see that for Murata capacitors is the same story. So at 1.1 volt, the capacitance will actually only be 16 microfarad. We needed 11, so this capacitor will work, but you know, this is a classic example where you can accidentally make a mistake and the capacitor will work not as intended. Okay, so I don't know, I would choose, in this case, capacitance needs to be, well, at least 10 microfarad. And then I select here, I order it by the capacity. Oops, something went wrong. Okay, so I would just want to select a capacitor which has the smallest size that fits my application. So I need something over 11. And this 0805 looks like it would work. So I would just pick one of these two capacitors because they have smaller size, so they will be cheaper, and their capacitance is higher than what I need at this bias voltage. So I will write it down here that in red, we had to select 22 microfarad capacitor to account for DC bias capacitance loss. Okay, so I write it down here. And basically I can just put that capacitor here between the signal and ground, and together with this resistance, it will work as a low pass filter. We don't actually need this second resistor. So it's kind of done. If we do this, then the microcontroller will see, instead of all of this noise, it will see something very similar to this blue line, right? The only thing that you would want to also check out is maybe its frequency response and its resistance at a certain frequency. As you can see, it's several ohms. So since the capacitor has series resistance, you know, maybe there's still some noise on top of it, but it's much, much less than the orange line that I drew. So this is how you would construct a filter. And you know, if you need a more complicated filter here, you will know it. Somebody else will tell you, or you will read it in datasheet that you would, you know, need a filter with a steeper cutoff frequency, for example, or something like that. But as far as I've seen the schematics, nobody wants to overpay for the filter. So usually the filter is just resistance and the capacitance, and that's it. And I will show you a little software trick, which is usually used to even more improve the analog signal filtering. And it is the following. So let's say we want to produce 10 samples per second, but what happens if I sample the signal, and even though I have this low pass filter right on that moment, maybe somebody turns on some motor in the grid, or maybe electricity makes a little bump or falls for a small period of time, or maybe a lightning strikes next to the house or something like that, and there's a little spike or little spike down. This capacitor has some internal resistance, so it cannot filter everything in the world. So maybe the electricity jumps or falls a little bit at the input, or the same effect would happen if microcontroller's power supply would make a short dip or short spike. because the voltage reference is connected to the power supply through some circuitry. So if the power supply jumps or falls or has some spikes, well, then voltage reference will also have a little bit less, because usually there's some fast reacting circuitry which filters it out, but still there will be some. So at times you will have a little bit wrong value sampled. And the trick that people do to filter these things out is the following. It will be a software averaging filter. So maybe in the beginning of lesson, you already wanted to tell me, hey, why don't we just sample many samples and then just calculate the average? It should filter out the, all of these spikes and noises. You have to use a low pass filter to avoid aliasing, because you can, if there's higher frequency than your sampling frequency, you'll always have weird off values, because you will always sample either above or below the average, and you will also always have wrong results. So you always use a low pass filter, or at least a small capacitor next to the pin, to filter out these very high frequencies. But you can use averaging to filter out some spikes that are not caught by this low pass filter. So I'll give you an example. And this will be the next layer. I'll just write it as 3. Use a software low pass filter, usually simple average. So you would use a software low pass filter inside your microcontroller, which is usually done as just calculating average. Some people use rolling average, some people use something else. I personally don't like these rolling averages because they usually have a shift. So the value goes down, rolling average starts to go down a little bit later. The average goes up, rolling average lags a little bit. So sometimes it's too fast, sometimes it's too slow. It just shifts the signal. But if you make several samples, you calculate the average of the certain window and you get in the middle of it, basically. So what you would do is you would make several samples per big sample and calculate average of that. So for example, if your sampling frequency is 10 samples per second, what you would actually do in the software is when it's time to make a sample, you very quickly sample, for example, 10 samples and calculate the average. So I'll write it like this. So you would, for example, you would have a timer in microcontroller which calls an interrupt after every 100 milliseconds. And inside that interrupt, instead of doing one sample, you write a small loop where you make 10 samples. In analog to digital converter, each sample takes only about 10 microseconds. So 10 samples would only take something like 100 microseconds. So it's 0.1 millisecond, and you have timer after 100 milliseconds. So you taking 10 samples asks for very little time, but you can do it. And then you calculate average and you will filter out these small spikes or you know, some higher frequencies that get through. You will also make sure that there's no mistake in the analog to digital converter, you know, maybe just makes sampling mistakes and so on. And the pro tip is you make these 10 samples and then you discard the highest and the lowest value. You discard one highest and one lowest value to get rid of some very small spikes. So, for example, you make samples. The sample values are, for example, 100, 99, 98, 99, 100. And then, for example, one of the samples is 300. So what you would do inside your software, you would just discard the biggest and the smallest, and you calculate average from the rest of the points. This way you automatically get rid of these sampling errors, for example, very short spikes and so on. So you can do this, and then you calculate the average from the remaining 8, for example, 8 samples, and yeah, and you get a very well filtered signal. And then, for example, in this heater case, on each signal, you would either use an on-off control or PID controller. Usually people use proportional integral differential filter, PID. In this case, it would be PID algorithm inside, in software. You can also construct PID regulators from analog signals, but microcontrollers are used if you want to configure them. You just write a new software. You don't have to change any component on the board. And for these PID regulators, proportional integral differential, if you're using this differential component, it's very important that the incoming signal is well filtered, because these small spikes can hit this PID algorithm, out of order, and it can produce very big oscillations on the output. So this is why it's important to filter these signals properly. And this is how it's usually done. Low pass filter and oversampling and discarding some outliers and averaging, and that's basically it. So do you have some questions about this? Okay, you can think about the questions about these analog filtering of the signals. And one of you asked me where to buy components, and I'll answer to this question now. So let's say I need a resistor of value 2.77 kilo ohms. The places where you can buy components in Europe without any taxes, and not really without taxes, you would pay taxes, but I mean without import, without paying some import duties in the postal service, is European or companies which have branches in Europe, or European companies which are distributors. One of them is, for example, tme.eu. This website, they are located in Poland, and they have a lot of components. And mostly you would use this website to buy some passive components, like, for example, capacitors, resistors. By the way, in this location, you would ask me, why are we using ceramic capacitors? Why don't we use electrolytical capacitors? electrolytical capacitors don't have this DC bias negative effect, but they are bigger and they can dry up after 10 years and then the circuit will not work. And also they take more space on the PCB. So usually people just try to use ceramic capacitors as much as possible. And if it's not possible, then they use these old school electrolytic ones. That's why. Okay, so here you can buy all of these things. You can also buy antennas. And usually the larger the thing, the cheaper it is here compared to other distributors. So you can buy a lot of things in this tme.eu located in Poland. You can buy as much as you want. Shipping costs €7.90. And all of the purchases, they have this 23% value added tax. So, you know, maybe you see some low price, but then when you buy it, you see that the price increased. It was because it initially, these websites are mostly made for companies. So initially they show the price without taxes, but you should select gross price, which means with tax. And so they have to apply Poland's 23% value added tax. In Latvia, the value added tax is 21%, so it's almost the same. And then the price increases a little bit. So don't have this bad surprise. So this is one place. Next place where you can buy is, which I know that has very fast shipping, is lv.farnell.com. They are located in United Kingdom, but they have warehouses in Europe, and they have maybe millions of customers in Europe. So even after Brexit, these guys figured out how to make some imports and exports offices in Europe, such that even though you are buying from Great Britain, they manage all the paperwork and they do all the imports, and you buy something here and you receive it to your doorstep with no papers at all. But shipping is €7. Previously, it was only something like €4, but because they have to manage all the import papers, it was increased after Brexit. But these guys ship, they have next day delivery of stuff that is in stock, right? So you find the chip, I don't know, some kind of, I don't know, processor. And if it shows it is in stock, then you will receive it tomorrow morning if you order today by some like 6 o'clock in the evening. So it says 260 pieces in stock. And if I just buy it, I will receive it tomorrow morning. So this is the fastest shipping ever that I know. Nobody ships as fast as Farnell. So you can use it as well. Next place where you can buy components is Mauser.com. They are located in United States of America, but they also have a branch in Europe. So even though you're buying from America, they do all the paperwork and you receive the goodies at your doorstep. Free shipping from €50. If you buy for €50, if your basket is €50, you get a free shipping. If less, then the shipping is something like €30. So you would use this thing only if you cannot buy stuff in these two places, and or if you need some special component which is not found anywhere else. And another thing is that if you need chips from Texas Instruments has lots and lots of chips. For example, the Q2050, 2450. For example, this battery charger, you can buy from Texas Instruments directly, and it's actually oftentimes the price is lower than in these other places. But shipping is €6, but they also do all the paperwork and all the imports. So you go here, you put it in the basket, you fill out your payment information, and you will receive the chips within something like 1 or 2 weeks. Of course, shipping from America takes a little bit of time, but within 2 weeks, you would always receive the chips. So if you need next day delivery, you would use Farnell. If you need some mechanical components, you would use DME. They don't have exactly the newest chips available, but plastic cases, passive components, antennas, very cheap here. And you can buy directly from Texas Instruments their chips. If you want parts from Wood Electronic, if you want to buy parts from Wood Electronic, you can buy directly from them as well, from this company. Shipping is €14, so maybe not the cheapest place in the shipping sense, but for bigger purchases, I don't know, if you buy tens of pieces, not just one piece, then their prices are up to 5 times lower than what these guys are asking. Because these Farnell and Mauser, of course, they put their own profit margin on top, and it can be pretty big. I've seen that, for example, an inductor costs in these places €2.50, but buying directly from Wood Electronic, it only costs 50 cents. So 5 times cheaper. So sometimes it's good to just buy from these Wood Electronic directly. And that's about it. And also, there is this digikey.com. You can buy from DigiKey. I think that DigiKey has the largest, absolutely largest stock of everything, but you need to correctly fill the registration form when you create your account. And if you do it correctly, they will import and they will pay all the duties and everything will work beautifully, and you'll receive your components maybe even within a few days, because they also have warehouses in Europe. But if you fill it wrongly, then you might have to pay extra money for the import duty as if you were buying from America or third world country. So when I bought from DigiKey last time, some years ago, I had to pay extra €50 to these import bureaus for some paperwork, and it was very disappointing. And the same thing goes to Arrow. There's this arrow.com. When I bought from them, I also had to pay extra taxes for the import from America, which was disappointing. Maybe something has changed, but I just don't use these guys. I can always find everything in TME, Farnell, Mauser, and Texas Instruments shop directly. So that's where I would buy parts. And if you want to order PCBs, the last place that I'm using is this outlier.net. You can order you can draw a PCB in something like Altium Circuit Studio or KiCad or anywhere, and then you can order them here. They are located in Germany, so again, no import fees, nothing. You just buy from them and get it delivered to you within 2 weeks, even if you use a regular post as shipping, which they have free shipping if sent by regular post, or if you want to send it in UPS and receive a few days earlier, you can use UPS for extra money, some like $26.99. They only produce boards with a thickness 1.6 millimeters, but they can produce 2-layer or 4-layer boards, and it's really convenient. previously I bought from this PCBWay.com from China, but the problem with China is that when these boards come to Europe, I need to pay extra 21% tax as value added tax, and then sometimes up to 40 or 50 euros to the shipping company which does the paperwork to import the goods in European Union. So buying from China is like importing goods, and it just a lot of paperwork. So even though you can see that, oh, the price is $5 for 10 boards, you can get in trouble because the local customs can say, hey, you know, you need to pay the tax. So, and in this Isler for a regular PCB, they charge 10 euros production fee plus something like 2 cents for every square millimeter or something like that. They actually have the price formula here. So I would normally order PCBs from this place and components from these places, and that's it. And I just solder them and use them. Okay, do you have some other questions?
So can you check the chat? I have pasted a link. Can you suggest?
Uh-huh. Let's check out. So you want to use this oscilloscope to watch some signals in the computer?
Because the other ones, the bigger ones, they are very, very costly, and the university has only allowed for purchase totally, including all equipments, 2,590, and I need to purchase everything within this range. But I think
Uh-huh.
this is the cheapest one, and I think it will be enough, right, for like I squared C signal analysis, or
Uh-huh.
will it be fine? Because I really do not have any previous experience with oscilloscopes.
Mhm. So the only thing that you probably are interested in initially is what is its bandwidth, which basically represents the maximum frequency that you can measure. 25 megahertz. Uh, if you're just using a microcontroller and nothing more, usually the microcontroller's maximum frequency is something like uh, 1 megahertz or 8 megahertz or 14 megahertz up to 48, but you don't really measure that signal. I think maybe for what you're going to do, this will be just fine. And in my experience, the 25 megahertz, let's check out. I'll multiply it with milli, micro, nano. So it's 4 nanosecond pulse. I don't know, maybe it's normal. What the oscilloscope that I'm using has 66 megahertz, and I'm measuring everything that I need. So I think it will be just fine for you, probably. Yeah.
So can you help me by can you Google and search the maximum frequency, or like the frequency for an ESP32 microcontroller?
ESP32.
Yeah, it comes in built-in Wi-Fi and stuff. So good
Yes,
IoT.
its internal clock is 260 megahertz, but you will never measure that signal. It's inside the CPU. External signals, I don't think that they will ever get over 10 megahertz of what you're going to do. If you are going to work with signals that have higher frequency, then somebody will be paying you enough money so that you can buy, more expensive equipment.
Yes, sir, I understand. And remember, sir, in the first class, when we were talking about battery circuits, and you were explaining to us the need for battery management, can you suggest a really good chip which will have all features such as a boost converter from 3.7 volts to 5 volts with a 1 ampere maximum current rating, and an overcharge protection, over discharge protection, with all these features. Because I tried in a lot of places Googling, I never found a one chip solution for this.
So you want something like you on the go USB?
I need a very small chip, or a very small chip that can allow me to boost the voltage from 3.7 to 5 volt with 1 ampere draw. Because I found many other chips, but they all were like 250 milliamperes output current, 300 milliamperes. I need around 1 amperes of output current.
Okay,
Yeah, the lithium
so
polyamide battery is 5 volts. No, the lithium polyamide battery that I'm using is 3.7 volts with
mhm.
1800 milliampere hours capacity.
Okay, so to be honest, I usually just select chips from Texas Instruments because they have many good chips. Their prices are really low, and sometimes I just find it here, and then I don't really look at other manufacturers because I'm lazy. But then maybe somebody else has something cheaper. But for Texas Instruments, I I would check out the following things. So first one is battery charger integrated circuits. So here in Texas Instruments, you will select, you know, under products, you select power management, and here's battery charger integrated circuits, and you will select products, and then you can just, check out maybe here is some chip that also has the boost converter. So it's very possible that some chip will have it. So USB on the go integration, maybe this thing has it. So let's check out the data sheet. It says that this thing can charge the battery, and it can also output USB on the go, 5 volts, 2.4 amps. So you can also configure it to give out less current, but it looks to me like this chip maybe does it. And maybe you can find in this list even cheaper chip. By the way, in Texas Instruments homepage, you can order the chips by price. I just start with the cheapest one, and then I look for until I find the cheapest chip that does what I want to do. So you can check out here, and also I think under features, control topology, interface, blah, 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 features. Maybe here's, you can check that it needs to be USB on the go integrated, 52 parts. So a lot of parts to choose from. I don't know, maybe this thing also has it. So you can, I would just find the chip that I need here. Also from Texas Instruments, as I mentioned, you found the chip. You can click order now, check out the inventory, and you can buy them from here. And shipping is just 6 euros plus maybe value added tax. So I would just find it here in the Texas Instruments homepage. But
Okay, so thank you.
you would go through several and read how they work, and then you would of course select the appropriate one. Now I just checked it out like
Yes, sir, of course. I will go through the Texas Instrument page and find the chip, and then maybe look for the same chip from the websites that you suggested.
yes, yeah, or you buy it from here or from those websites, however you feel good. And by the way, one way to look for components is using Octopart. Let's say I found this chip and then I want to buy it. I would copy its part number and I would paste it in Octopart. And here it automatically searches through the largest internet shops, and it shows you stock availability and the price. So you can see, oh, you're buying, for example, your favorite shop is Mauser. You see it has 4,000 pieces at this price. Texas Instruments has at this price, this many pieces, and so on. So Octopart is a really good place to
Yes,
use.
it's really good actually. It will make it a lot easier to find the parts. instead
Mm-hmm.
of going to individually those websites and searching.
Yeah, I have talked to representatives of these other internet shops, and they don't like people using Octopart. They say that Octopart only refreshes information once a week or even less frequently. So maybe this information is out of date. But what I think is maybe they just don't want you to search here, so you would see that their rival has a lower price and you would buy from their
Yes.
rival. But you know, of course, you would check the availability in the real website when you buy it.
Okay. Yes.
Okay, some more question.
Probably yes, but not at now because now only I'm starting to work. It's a 5 month project. I
Mm-hmm.
might ask you other questions as well while designing.
Okay, yeah, we will keep in touch.
Thank you, sir.
Mm-hmm. Please, you're welcome. Yeah. Um, some more questions, some more comments. Okay, if no more questions, then we can probably finish this lesson today. Um, and we meet after 1 week next Monday, Tuesday, Wednesday, and we keep studying. Okay. So goodbye.
Okay, goodbye.